All right, guys, we're going to be looking at polynomials, and we're going to determine some of the characteristics of just basic analyzation of the polynomial. And in this case, I'm giving you over on the right-hand side a graph of what is a cubic, and on the left, I've got some questions that we're going to work through. I am going to work through them all. Hopefully, the video is not too long, but you can always skip ahead and play it faster. So, first thing is we're going to determine the degree of a polynomial, and I've already told you that it is a cubic, but if we needed to identify that it was a cubic, it's nice and easy. We just go to the x-intercepts that are there. There's our x-intercepts. That is actually one of our questions. So when I do that, I say, okay, well, there are 3 x-intercepts in this case, and not going too deeply into multiplicities, we have 3 x-intercepts. That means that this is a degree 3 polynomial. And so that's what I'm gonna put here, degree 3, which means we're talking about x cubed. While we're here, we can jump down to the bottom and we can determine the x-intercepts because we've already pretty much done that. We are going to, let's go ahead and click on those x-intercepts, which will be at -5. 3, and 7. So writing on that, x-intercepts will be -5, 3, and 7. And while we're here, we can just go for the y-intercept. Wow, boom, -210. -210, remember y-intercept is on the y-axis, okay? So we're gonna go to this new phrase we call local minimums and local maximums, okay? And a lot of people get them confused because when we talk about local minimums and local maximums, we're talking about to specific regions, okay? So a local minimum isn't down here all the way down at -infinity because it just keeps going down and down and down and down. It's where it decreases and then begins to increase again, kind of like a parabola would be, okay? And so in this case, I look for a local minimum. I follow out the graph. It drops down, boom, it begins to increase. There's a local minimum, which is -1.9. Okay, so local minimum of -1.9, comma, -270.4, -270.4. And then after that, we go to local maximum, same idea. We're looking for the fact that it's not going up to infinity. We don't care about that. We're just looking for a region in which we see a maximum. And if we look at that, we can trace it up. It's increasing and then it decreases and it look right there. So it looks like we have a local maximum at approximately 5.2 and 80.8. And that would be a local maximum. And so then we are going to go off and describe the domain of this. Okay, so the domain, as you can see, and we've talked about this in previous classes, okay, are all the x values. Okay, so we're looking for x values. Okay, and all the x values that make the graph occur. Okay, so if I am tracing this out in this direction towards -infinity, well, guess what? There's always going to be a graph. Okay, so when we do this domain, we always say, okay, well, let's go back to the idea we have -infinity and we have +infinity. And you'll notice that in this domain, -infinity on the x, all the way down there will produce graph. All the way up, +infinity will also produce graph, okay? And you should also see as we do that with the range or the y values, okay? It's easier to tell with the y because we can just keep tracing that thing up. It keeps going up and up and up. And then it also keeps going down and down and down and down and down and down and keeps on going down and down and down. And then so what we know is the range is going to go from -infinity to +infinity as well, those y values, okay? Describe intervals of increase and describe intervals of decrease. Here's probably the most complicated one, and it's not that complicated because all we have to do is trace that graph from left to right, okay, and see what's happening. So I'm going to do this in multiple colors, okay? If we look at this, it is decreasing from here to there. That is decrease, okay? And then after we do that, check it out. It is increasing. Okay, and then after that, it is decreasing again. Okay, we just follow it out. So when we write intervals of increase or intervals of decrease, we just use the x values. So let's see here. I'm going to do the increase one because that's the first one on the statement. Check it out. From here to here, it is increasing. And that x value we can find right here from the local minimum and the local maximum. So it's increasing from negative 1.9. Okay, so roughly negative 1.9 all the way until it gets to 5.2. Then we have to, and remember we're using interval notation, then we do decreases. Well, it's decreasing, it's decreasing from here out. So it's coming down this way, right? Well, so it's decreasing from negative infinity on the x, negative infinity is down here, all the way until we get to this local minimum. We said that local minimum was negative 1.9. And then we just put another statement, or we pick it back up for a decrease at 5.2, which is right here, right? And then it decreases until we get all the way out to infinity, okay? Now the last one we want to do is we want to get this end behavior statement, okay? That's this right here, end behavior. We've talked about this before as well. As we do the end behavior, it's really important to notice the notation because that's the part that messes with people the most, okay? And the end behavior is just simple in the sense that it says, okay, as x goes to negative infinity, which is moving left, as we go left, what happens to the graph? The graph is going up. So as we go left, graph goes up. That's what this whole entire statement says, okay? And then what we do is we says, well, since it's going up to infinity. So as x, as we look left towards negative infinity, what happens to the graph? Graph goes up. Does what? It's supposed to be an E. Okay, in this case, it goes up. Okay, so what we're going to do now is it increases. We do the exact same thing, but we do it on the other side. And it says, as x approaches positive infinity. Well, positive infinity is out here. And then it asks the same question. As we go to positive, so instead of as we look left, it's as we move right. So as we look right, what happens? So as we look right, what happens? It goes down. It goes down to negative infinity. And that's how we do all these characteristics of polynomials.